Well, students, you people are preparing well for your board classes, I think. Now, due to Corona and all, you are getting a lot, many time for your preparations and all. So I can give you some tips related with your first lesson so that your preparation will be too fruitful. So we can see the chapter that is relations and functions. So to study about relations and functions, we have to revise a bit from your 11th standard. Nothing else, sets. What is a set? You people are knowing set is a collection of data. See my whiteboard. Set is a collection of data. Set A is equal to 1, 2, 3, 4. And the same way, set B is equal to 5, 6, 7, 8. The members of that set, the data, the elements of that set. So later on, we studied a lot regarding different types of sets, or roster form, set builder form, empty set, universal set, subsets, and cross products. A lot many things we studied, and along with that, two more concepts we studied there at 11th standard, that is relations and functions. Again, in the case of relations and functions, we studied one more thing, that is Cartesian product, that is cross product, Cartesian product or cross product, Cartesian product or cross product. Nothing else. If the set A is equal to 1, 2, 3, 4, and if the set B is equal to 5, 6, 7, 8, then A cross B is equal to set 1, 5, 1, 6, 1, 7, 1, 8, 2, 5, 2, 6, 2, 7, 2, 8. Likewise, 3, 5, 3, 6, 3, 7, 3, 8, 4, 5, 4, 6, 4, 7, 4, 8. That is a Cartesian product, cross product of set A and B, that you studied already there at 11th standard. Nothing new. Again, we are going to study from this what is a relation. With the use of this cross product or Cartesian product, we are studying about a relation and functions. From here, A cross B, a relation from set A to B, we can write in a huge way, in an unlimited way. Relation from set A to B, that can be again that can be represented by A or B. Just you can see that bracketed matter there in the whiteboard. A or B, A related with B. So that A or B, of course, that will be the subset of A cross B. What are the subset of A cross B? A cross B itself is the subset of A cross B, and null set is also a subset of A cross B, and an unlimited and a lot many subsets we can write in some particular way. For example, R is equal to AB such that A and B are both even. A and B are both even, whereas A belongs to A and B belongs to B. So what is the answer for that from the question? 1, 2, 3, 4. A and B must be even numbers. So from set A, even numbers are 2 and 4 only, and set B, even numbers are 6 and 8 only. So clearly you can write what is the set R. What is the set R? That is 2, 6, 2, 8. Likewise, 4, 6, 4, 8. Only 4 members are there. So that is the subset of A cross B. So that R is a relation. Again, A, B such that A and B are both odd numbers, whereas A belongs to A and B belongs to B. Clearly it is 1, 5, 1, 7, 3, 5 and 3, 7. Likewise, a lot many ideas we can declare, we can represent by the use of different subsets. These subsets are called relations from set A to B. I think you people are very clear about this. And see the number of elements in A, that is equal to 4, and B is also 4. So how many subsets you can prepare, that also you studied there in 11th standard. If the number of elements in A is 4, or let us consider number of elements in set A is equal to P and set B is equal to Q, then the total number of subsets will be 2 raised to the power P into Q. That formula we studied already. So with the same formula, we can find out the number of relations over here. Here set A is having only 4 elements and set B is having only 4 elements. So total number of relations there in A cross B, that is in total number of relations possible, is equal to 2 raised to the power 4 into 4, that is equal to 2 raised to 16. 2 you have to multiply 16 times. So this is the revision regarding relation which we studied there at your 11th standard. So students, you are very clear about relations, I think. Now we are going to have another topic, that is functions. Before going to study about functions, we have to get a clarification regarding one important topic, that is ordered pair. See, there at the studies of relations and functions, we study one cross product. There a lot many bracketed elements, grouped elements we are seeing, 2, 6, 2, 8, 1, 5, 1, 6, 1, 7, 1, 8, and 3, 6, 3, 7, 3, 8. Like that, a lot many grouped elements we are seeing. The grouped elements have 2 elements inside, first one and second one. That first element came from first set and the second element came from second set. Always the first element will be from first set and second element will be from second set. That is why it is called an ordered pair. Remember that technical term, ordered pair, that you will see in future a lot many places. Now functions. What is a function? Nothing else. It is a pure relation only. A function is a relation. Don't be confused. All relations are not functions, but all functions are relations. How? See, a relation in which no 2 ordered pair have same first element, that is called a function. There should not be any 2 ordered pair with the same first element. That is my concept. That is my explanation. That means each element of A has one and only one image in set B. There should be one and only one image in set B. The person who is standing there at the bus stop, if he want to go for Delhi, he cannot catch the bus for Trivandrum. Clear? Means if he want to go for Delhi, he have to catch the bus for Delhi only. He cannot catch the bus of Trivandrum. Both are of opposite sides. In the same way, there should be only one image for a pre-image. So what is pre-image and image? They are in the ordered pair in a function. The first element is called pre-image and the second element is called image. So for a particular pre-image, there should be only one image. Here we are seeing a lot many relations down there at your whiteboard. First of all, a relation where A and B both are even numbers, that is 2, 6, 2, 8, 4, 6, 4, 8 only, that you people are knowing how to write the relation with even numbers 2, 6, 2, 8 to 4, 6, 4, 8. See, both ordered pair, first ordered pair, the first element is pre-image is 2 only, and image is 6 and 8. That is not possible there in the case of function. That is why it is not a function, it is a relation only. Second case, ABR, if ABR both odd, then it is 1, 5, 1, 7, 3, 5, 3, 7. For 1 we are seeing 2 images, for 3 again we are seeing 2 images. That is why it is also not a function, that is a pure relation only. Clear? So there in the case of relation, the first element is, the set of the first element is called domain, and the set of the second element is called range. See, domain is the set of first elements of ordered pairs, and range is the set of images, set of second element of ordered pair. So domain and range are both are sets, but pre-image and image both are individual elements. 6 is the image of 1, there at the case of function 1 is the pre-image of 6. Both difference also you should have to understand from this notes. So pause the video and note it down at your copy. Start. So students, you people are very clear about relations and functions. Still, if you are confused anywhere, should contact me, don't hesitate. Now we are going to we are going to study about different types of relations. Relations are of different types. See, set A is equal to 1, 2, 3, 4, B. We are avoiding that B, and we are preparing a Cartesian product. Can you prepare a Cartesian product of set A is equal to 1, 2, 3, 4? Of course, we can prepare a Cartesian product of set A is equal to 1, 2, 3, 4. Cartesian product, a relation between relation you can write for a set A, that is A cross A, a relation that is a subset of A cross A, that is the relation of set A. So if it is 1, 2, 3, 4, A is equal to 1, 2, 3, 4, A cross A is equal to what? 1, 1, 1, 2, 1, 3, 1, 4, 1, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4. And 4, 1, 4, 2, 4, 3, 4, 4, that will be the whole set, universal set of A cross B. The all elements are there. Clear? So from that we can make many subsets, that is also 2 raised to 4 into 4, that is 2 raised to 16 subsets you can prepare. That 16 subsets are 16 different relations which will give 16 types of ideas ahead of you. Clear? From that relations that can be classified into different ways, that we are going to study here in your 12th standard syllabus. Types of relations. First type is null or void or empty relation. If there isn't any element there in the subset, there in the relation, that type of relation is called the empty relation. That word itself will provide you the correct meaning of empty relation, void relation, null relation. There should not be any element there in the set, there in that relation. That relation is called the empty relation. For example, there A is equal to 1, 2, 3, 4. If I will write a condition B is equal to A plus 5, B is equal to A plus 5. Let us consider A is equal to 5, 1. A is equal to 1. 1 plus 5 is equal to 6. 1, 6 is possible? Is there any element there in the universal set 1, 6? No. And if it is 2, then 2 plus 5 is equal to 2 plus 5 is equal to 7. That 7 is not there in A. That 1, 7 is not an ordered pair there at the cross product of A cross B. So it is not an ordered pair of the relation there in R. So that R is what? An empty relation. There should not be any element with the condition B is equal to A plus 5. For example, if there is a boys' school, can you prepare a set of girls over there? No. It is not a co-education school. Their girls may not be there. So if I want to write a set of girls of a boys' school, then it is not possible. Likewise, here the elements of R is null. It's empty. It's nothing is there. So we can say it is an empty relation. Are you clear? Then that is universal relation. Each element of a set related to every element of set to another set. From here, set A only. So that is why we can say each element of a set A is related to each element of A. So that type of set is called universal set. So let us consider one example, A, B, such that A minus B greater than or equal to 0, whereas A belongs to A and B belongs to A. Both A and B are belonging to A only. A minus B is no greater than or equal to 0. That A minus B, not A minus B only, it is modulus of A minus B is greater than 0. That is the condition over here. So let us see the ordered pairs of A cross A, that universal set. 1 minus 1 is equal to what? 0 only. So it is satisfied. Then again 1 minus 2, that is 1 minus 2 is equal to what? Minus 1. Modulus of minus 1 is equal to what? 1. That 1 is greater than 0. Again 1 minus 3, that is equal to minus 2. Modulus of minus 2, that is equal to 2 only. That is also greater than 0. If you will consider each and every ordered pair of that universal relation, then you can find each and every element of set A is related to each and every element of set A. That is why the set R is a universal relation. Are you clear, everybody? Now the third set, that is identities relation. That is not that much important. Still, you can understand this one set A and cross A. If you will consider some ordered pairs like 1, 1, 2, 2, 3, 3, 4, 4, then what we can say that? That is called identity relation. A and A, both pre-image and image, should be equal. Such type of identity relation is called identity relation. So 1, 1, 2, 2, that is an identity relation. 1, 1, 2, 2, 3, 3, that is another identity relation. 1, 1, 2, 2, 3, 3, 4, 4, that is another identity relation. So this is called identity relation. Now the next type of relation, that is a reflexive relation. That is a reflexive relation. That is the main important topic which we have to concentrate upon. The next three relations are reflexive, symmetric and transitive. These are the three relations, three types of relations which we have to concentrate upon. So students should pay your attention much more over here for the examination point of view. This much things I explained, that is for your knowledge, that is for your good awareness, for that purpose only. Now for the examination point of view, you have to put your stress upon a reflexive relation. What is a reflexive relation? A relation R is reflexive. That means R is a set A such that for every A there should be an image A itself. For every A, there should be an image A itself. Each element of A, each and every element of A must have an image A itself. Forever, each and every, that line, that words you have to stress upon. 1, 2, 3, 4 R. See the examples are 1, 1, 2, 2, 3, 3. Set A, 1 is there, 1, 1, 2, 2, 2, 3, 3, 3, again 4, 4 also should be there. Every element, there should be an image. That image should be the image only. That is the definition of reflexive. So the first relation is not a reflexive, but it is identity relation. Then second, 1, 1, 2, 2, 3, 3, 4, 4. 1, 1, second element 2, 2, third 3, 3, 4, 4. So all elements are there. All ordered pairs are there for each and every elements of A. So it is a reflexive relation. Next relation you can see 1, 1, 2, 2, 3, 3, 4, 4, 1, 2. Here 1, 1, 2 extra is there. No matter. You have to see the ordered pair of particular elements of A is there or not. Every element of A is there or not. And the pre-image and the image are equal or not. These two conditions only you have to verify. That is verifying there in the third case. That is why that relation is also reflexive, but it is not identity relation. 1, 2, both are not same. That is why it is not identity relation. So I think you people are very clear in reflexive relation. Are you clear? Yes, of course. Thank you. Now the next type, that is a symmetric relation. Here again some more conditions are there. What is that condition? If A1, A2 is there in the relation, carefully you have to listen. If A1, A2 is there in the relation R, there must be A2, A1 also. It's opposite. It's a reverse relation. That you are going to study over here. Relations, reverse relation. That also we are going to study in this area. A1, A2 is an ordered pair in the relation. That means A2, A1 is also an ordered pair of the same relation. Must be an ordered pair of the same relation. So such type of relations are called symmetric relations. So with the examples you can study much more. See, first relation 1, 2, 2, 3 and 1, 1. See, 1, 2 is there. Then what should be? 2, 1 also must be there. First elements only. One ordered pair you have to check. 1, 2. Then you have to see 2, 1 is there or not. No, 2, 1 is not there. So clearly you can write this is not symmetric. And then further elements 2, 3, 1, 1 you don't want to check even. But we are going ahead 2, 3. Then 3, 2 is also not there. 1, 1 is there. Then 1, 1 means 1, 1. Both are there. 1, 1 means both elements are same. That is why its reverse order is also there. But there are 2, 3 and for 1, 2 there isn't any reverse ordered pair. So it is not a symmetric relation. Second one 1, 2. Then 2, 1 is there. 1, 1, 1, 1. 2, 2, 2, 2. 3, 3, 3, 3. Everywhere that reverse order we are seeing the relation. That is, it is purely symmetric. 1, 2, 2 1 is also there now. 1 1, then if we will make the reverse order, then 1 1 itself will be the answer. So 2 2 is the same way, then 3 3 is also. So we can say it is symmetric, but it is not reflexive. Why it is not reflexive? Because 4 4 is not here. Now third relation, 1 2 2 1, 2 3 2 3 2 3 2 3 2 3, then 3 2 is not there. So you don't want to go ahead, that is not a. Then again the fourth relation, 1 1 1 1 2 2 2 2 3 3 3 3 4 4 4 4, then 1 2, then 2 1 is there. But next C ordered pair, that is 2 3. For that 3 2 is not there. That is why it is not symmetric. But it is reflexive, because 1 1 2 2 3 3 4 4, each and every element of A is having its image, and both image and pre-image are equal. So we can say it is reflexive. And 2 1 1 2 and 1 2 and 2 3 are extra over here. We don't want to see all that. We have to see each and every elements of A have its image or not, equal image or not. That much only. According to that concept, this is reflexive, but it is not symmetric. Then now see the fifth one, 1 1 2 2 3 3 4 4. 1 1 1 1 2 2 2 2 3 3 3 3 4 4 4 4. Everywhere, if you will change the order, we are getting the same ordered pair over there. And each and every elements of A, we are getting the image also. That is why it is symmetric and it is reflexive also. It is symmetric and it is reflexive also. Again, we are going to study one more topic over here, inverse of a relation. Just you can see the whiteboard. There one relation R is equal to 1 2 2 1. 1 1 2 2 3 3. If you will write if you will change the order of the ordered pair, what will be the result? 2 1 1 2, then 1 1 2 2 3 3. Both R and R inverse are equal. So what we can say, if R and R inverse are equal, then it is symmetric. See the definition for symmetric relation. A relation and its inverse relations are same, then it is a symmetric relation. Otherwise it is not a symmetric relation. See the fourth relation, 1 1 2 2 3 3 4 4, 1 2 2 1 and 2 3. There 2 3, if you will write the inverse, then 3 2 also must be there, no? That is why it is not symmetric. So here you are very confirmed about symmetric relation, I think. Then we will go ahead. Just you can revise these topics once more after noting the things there at your copy. And if you have any doubts, you can contact with me. Now the next type of relation and last type it is here in your syllabus, that is transitive relations. Transitive relation means if AB is an ordered pair of the relation R and BC is also an ordered pair of R, then AC must be there. See, if AB is an ordered pair of a relation and BC is also an ordered pair of the relation, then AC must be there in that relation. That is called, if it is there in that relation, then it is called transitive, otherwise it is not a transitive relation. We will see with the help of examples and all. It is too confusing. So with the examples, it should be very clear. See, relation R is equal to set 1 2 2 3 and 1 1. 1 2 is there. Then 2 3 is also there. But 1 3 is not there. See, AB, that is 1 2. Then BC, that is 2, 3. 1, 2, then 2, 3. AB, then BC. Then AC must be there, no? 1, 3 must be there, no? 1, 3 is not there. That is why it is not transitive. Are you clear? Then let us consider it is symmetric or not. 1, 2 is there, 2, 1 should be there, 2, 1 is also there. That is why it is not symmetric even. 1, 1 is there, but 2, 2 is not there, 3, 3 is not there. That is, it is not a reflex. See the second one. 1, 2, then 2, 1 is there. That is why 1, 1 is also there. So AB, BC, AC is satisfying over there. Again 2, 1 and 1, 1 is there. Second and the third, 2, 1 and 1, 1 is there. So 2, 1 and 1, 1, then 1, 1 is also there. Again 1, 1 is also there. That is why that is also satisfying. Again 1, 1, 1, 1, 1, 1, 1, 1. So AB, BC, AC, all these three things are clear. Then 2, 2 also same things. 2, 2, 2, 1, 1, 2. In that way also you can consider. Yeah, 2, 2, 2, 2, 2, 2. That way also you can consider. Then 3, 3, 3, 3, 3, 3, 3, 3. In that way, if you will consider it is every 3 cases are there. Then 1, 3, then 3, 3, 1, 3, then 3, 3. Then 3, 3 is also there. So it is transitive. All the elements are satisfying the condition. AB is a member of A, R, and BC is a member of R. Then AC is a member of R. So that this is transitive. Second, let us see it is it is symmetric or not. 1, 2 is there, 2, 1. 1, 1 is there, 2, 2 is there, 3, 3 is there, 1, 3 is there, but 3, 1 is not there. That is why it is not symmetric. Reflexive, 4, 4 is not there. That is why it is not reflexive. Clear? Then next third one, 1, 2 is there, 2, 1 is there, then 1, 1 is also, that is there. Then 2, 1 is there, 1, 2 is there, then 1, 2 is also, that is also correct. Then 2, 3 is there, then 3, 3 is there, then 3, 3 is there, that is also correct. 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 3. So it is transitive totally. Then it is not symmetric because 4, 4 is not there. And it is not, it is not symmetric because what? Because what? 2, 3 is there, but 3, 2 is not there. And it is not reflexive because 4, 4 is not there. Again, we will go for the next relation, that is 1, 1, 2, 2, 3, 3, 4, 4. Everywhere we can see that conditions. Then 1, 2 is there, then 2, 1 is also there, then 1, 1 is also there. Then 2, 1 is there, and 2, 2 is also there, then 1, 2 is also there. And 2, 3 is there, then 3, 3 is there, again 3, 3 is also there. That is why it is transitive, but it is not symmetric. Why it is not symmetric? 2, 3 is there, but 3, 2 is not there. Am I right? Yes, of course. Then the next one, reflexive. It is reflexive also because 1, 1, 2, 2, 3, 3, 4, 4. All 4 are available over there. That is why it is reflexive. Then the next case we can see 1, 1, 2, 2, 3, 3, 4, 4. All 4 cases are there. And next one is 1, 2. 1, 1, 1, 2. So and 1, 2. That is why it is transitive. But it is not symmetric because 1, 2 is there, 2, 1 is not there. And it is reflexive because all cases 1, 1, 2, 2, 3. Are you clear, everybody? So all types of relations we studied already. You are very convinced. We will make you clear the doubts. Now, at the end, we can have one more concept over here, that is equivalence relations. Equivalence relations. If a relation is reflexive, If a relation is symmetric and if a relation is transitive, then it is called a equivalence relation. For example, one question I can give to you. See the whiteboard. Let T be the set of all triangles. Let T be the set of all triangles in a plane with a relation R. That relation R is a relation in T given by R is equal to T1, T2 such that T1 is congruent to T2. T1 is congruent to T2. Set T, many triangles are there. T1, T2, T3, T4 like that. You have to prepare a relation that R such that T1, T2, where T1, T2 are congruent. So you have to prove that the relation is equivalence relation or not. First of all, if you want to prove that this is equivalent relation, you have to prove that this is reflexive, this is symmetric, and this is transitive. So relation is reflexive. We are going to consider that means that T1 and T2 is congruent. T1 and T2 is congruent. All the triangles are congruent. So T1 and T2 congruent. That means T1, T2. That will be an ordered pair. No, not T1 and T2. T1 will be congruent to T1 only. T2 can be congruent to T2. T3 can be congruent to T3. T4 can be congruent to T4. Means, see the condition, T1 is congruent to T2. Each and every triangle is congruent. Such congruent triangles relation it is. So, T1, T2, T3, T4, many triangles are there. One triangle is congruent to the same triangle. No? That is why the relation is reflexive. T1, T2 will be an ordered pair. T1 will be an ordered pair. T2 will be an ordered pair. T3 will be an ordered pair. T4 will be an ordered pair, because one triangle is congruent to the same triangle. That is why it is reflexive. Are you clear? Now, symmetric. See, if T1 is congruent to T2, triangle 1 is congruent to triangle 2. So T1, T2 will be there in the relation. If triangle 1 is congruent to triangle 2, then triangle 2 will be congruent to triangle 1. No? So AB and BA is also there. That is why it is symmetric. Now the third case, that is transitive. See, T1 is congruent to T2. Then T2 is congruent to T3. So T1 will be congruent to T3. No? T1 is congruent to T2. Then T2 is congruent to T3. Then T1 and T3 also should be congruent. No? That is why it is transitive. So our relation is equivalence. Why? Because it is reflexive and it is transitive and it is symmetric. And here at the end we are going to study one more important topic over here, that is equivalence class. That is very, very difficult. That is very difficult to understand. Just to go through the whiteboard, both things. One example also I written over here, and what are the rules under equivalent class, that also I written over here. If I will tell directly the rules for equivalent class, then you cannot understand the matter properly. So we are going to study with the help of an example over here. Show that the relation R in the set Z. Z means number in integers. Integer Z is the representation of set of integers. Show that relation R in the set of integers given by R is equal to AB such that 2 divides A minus B is equivalence relation. 2 divides A minus B is equivalence relation. See, we are going to prove that it is equivalent relation. First one, if you will consider set of integers 1, 1, 2, 2, 3, 3, 1 minus 1 is equal to 0, 0 divided by 2 is equal to 0, so it is divisible by 2. You are getting an answer as 0. 2 minus 2 is also 0, that is also divisible by 2. That is why what we can say, if you will write each and every ordered pair with the same first pre-image and image, then it is divisible by 2. That is why it is reflexive. Then now we are going to see A minus B is equal to A minus B is divisible by 2. Let us consider A minus B is divisible by 2. Then B minus A is also divisible by 2. A minus B is something and B minus A is also something. There the difference is one negative and a positive. Am I right or not? It can be negative or it can be positive. So what we can say, every time it should be divisible by 2. So it is symmetric. A minus B is divisible by 2 and B minus C is also divisible by 2. Then of course A minus C is also divisible by 2 because A minus B plus B minus C, that is A minus C only. B and B you can cancel, then you can write it is A minus C only. That A minus C is equal to what? That is a factor of 2. That is proved by the use of this steps. A minus B is equal to 2A, that is 2R. Just you can consider A minus B is equal to 2R, a multiple of 2. There you can prove by the condition only. It divides 2. It divides 2 means that is A minus B is something multiplied by 2. Then B minus C is also something multiplied by 2. Then if you will add together A minus B plus B minus C, then what you are getting? 2R plus 2S, that is 2R plus S, that is 2 is a factor over here. So A minus B is also a multiple of 2. That is why this is transitive. All these 3 cases are highly clear in front of you. If it is clear, then it is equivalence relation. So in this equivalent relation, I am dividing this cross product, this Cartesian product, into 2 categories, 2 group, which is 2 independent group. For example, even integers containing 0 are the pre-image. Even integers containing 0 are the pre-image. There what will be the ordered pair? 0 plus 2, 0 minus 2, 0 plus 4, 0 minus 4, 0 plus 6, 0 minus 6. Like that you will get a huge number. Integers you want to consider. There 0 plus 2, 0 minus 2, 0 plus 4, 0 minus 4, 0 plus 6, 0 minus 4. That will be the first category. Second, if you will divide that relation into another group, if you will divide another group, you will get with odd integers, with containing 1 of the first elements. So 1 plus or minus 3. 1 plus or minus 5, 1 plus or minus 7. If you will do the subtraction everywhere, you will get a multiple of 2. It can be divided by 2. So there in both category, the elements are closely related. How? Everywhere the ordered pairs, the difference of elements in each and every ordered pair, it is a multiple of 2. It can be divided by 2. And second category 1 3 1 5. If you will do 1 3, 3 minus 1, 1 minus 3, that is equal to what? Minus 2. Minus 2 can be divided by 2. 1 5, 1 minus 5, that is equal to minus 4, that also can be divided by 2. So there is also a relation. So two category you got. The two category is what? Even integers containing 0, that can be represented by a square bracket 0, equivalence class square bracketed 0, that is 2r. Then odd integers containing 1, that is also an equivalent class with square bracketed 1, that is equal to 2r plus 1. Two classes you prepared over here. There isn't any relation between these class, but there is a relation in an interrelation there in each class. There isn't any intra-relation between the class, but there is an interrelation between the members, ordered pair of a class. So these two classes are called, this type of classes are called equivalent class. Now compare your answer with the rules of equivalent class. What are the rules of equivalent class? There is a relation, there is an equivalent relation in an arbitrary set of X. Equivalent class is an equivalent relation with an arbitrary set X. Arbitrary set X means what? Question itself is a set of Z integers, set of natural numbers, set of real numbers, set of whole numbers. That is arbitrary set of X. See, our relation is an equivalent relation with the arbitrary set of integers. So first topic is clear. Relation is equivalence with the arbitrary set of integers. Then that relation divides X into mutually disjoint subset AI such that all elements of AI are related to each other. See the first clue of the second rule. What is that second rule? R divides X into mutually disjoint subjects. R divides into mutually disjoint subsets AI such that all elements of AI are related. See, we are dividing this into mutually disjoint subsets, disjoint subject, even integers, odd integers. There isn't any common ordered pair over there. That is why it is called the mutually disjoint subject. And there is an interrelation there in each and every subset. First subset, second subset. Interrelation is there, but intra-relation is not there. What is the interrelation? It is divisible by 2. There isn't any intra-relation. Why? Then second, element of AI is related to any element of AJ, means both subset doesn't have any relation. I and J, you should not be equal. There should not be any relation between these two classes, two subsets or two or more subsets. Such type of subsets are called equivalence relations. So this much only about equivalence classes and all. And finally, I am concluding this chapter with a short topic which is not that much important. Still, you must have to remember, that is anti-symmetric. Anti-symmetric means if AB is a member of a relation, and BA is also a member of the same relation, then A and B should be equal. That type of relation is called the anti-symmetric relation.